Hello everyone, and thanks for watching Edupedia World videos. In this video we'll learn about motion in one dimension and we'll use concepts of calculus which we've learned previously. There are two different aspects of studying the motion of a body, and they are kinematics and dynamics. Kinematics is the study of motion of a body where it's not concerned with the cause of motion. This is what we'll focus on right now, and all we'll really be concerned with is how the body moves, what is its position at a certain time, what is its velocity at a certain displacement, and so on. We'll not really be concerned with the cause of motion, which is another word for the forces. And the study of causes of motion along with the study of motion of a body is called dynamics, and we'll do that once we reach Newton's laws of motion, but right now we'll just focus on the study of motion of a body. In this particular video, we'll focus on motion in one dimension, and that too for a very specific set of cases. We'll focus on motion completely in a straight line. That means motion will occur only in one dimension, not on a plane. We'll focus in this video basically on motion with a constant acceleration. Now we've studied motion with a constant acceleration before, but we'll really focus in this case in deriving these equations, because in the next video we'll move on to motion with variable accelerations, and we'll need to be able to derive every equation for any sorts of acceleration. And then motion with constant acceleration will just be a subset of that case. And we'll be focused on speeds which are much smaller than the speed of light. Once we reach the speed of light, the normal rules for addition of velocity do not really apply, and another set of theory is needed, which is called the special theory of relativity. So we'll not focus on that, we'll just focus on speeds much smaller than the speed of light. So let's start. So we will draw an x-axis and we'll consider the motion of the body on this x-axis. We'll take one point to be the origin. Generally we take the origin to be the point where the particle is at t is equal to 0, but that's not necessary. And in this case we'll assume that it started from the origin and it is at a position x at time t. So let's say we know x as a function of t. That means you give me any time and I will be able to tell you, based on information I have, what the particle's position is at the moment. Theoretically, we could also be able to calculate the velocity at any point, because all we would need is the position at a point and a position at a point which is slightly after that, and we will be able to calculate the difference in position divided by the difference in time, and we would get the velocity. And then we would also be able to get the acceleration in this manner. So the first important thing to know is, if I know the position of the body at any point of time, I know everything there is to know about the motion of the body. Right? And we'll eventually see how to calculate all the properties. The definition of velocity is change in position by change in time, which would be x2 minus x1 by t2 minus t1. If the particle is at a position x1 at time t1 and it moves to x2 at time t2. But this is not always the velocity, it has a very special word. This is called the average velocity. And the average velocity is always taken between two finite instances of time, and we take the displacement between the two times, we take the difference in the times, and we divide the two. There is another quantity which is called the instantaneous velocity, and it is defined as dx by dt. And we saw in the last lecture that to calculate the change between two events, we use delta x by delta t. But if we want to calculate the change at a particular point, then what we do is we calculate the change between 2 points very close to each other, and we make sure those points eventually end up coinciding by making sure that dx goes to 0. And that is called differentiation. So the derivative of position with respect to time is the velocity at any instant of time. Remember, the average velocity is defined between two separate instants of time, whereas the instantaneous velocity is defined for a particular instant of time. Similarly, the relation between position and velocity is analogous to the relationship between velocity and acceleration. So we can deduce that the average acceleration would be delta v by delta t between two finite instances of time, and it would be v2 minus v1 by t2 minus t1. whereas the instantaneous acceleration again defined at a point of time, is dv by dt. The derivative of the velocity with respect to time. By the way, these are always actually defined between two instants t1 and t2, not t. This would also be actually t1 and t2. Whereas instantaneous velocity and instantaneous acceleration are defined at a particular time. And how do you calculate them? We'll see it in much more detail in the next lecture. But all you need to do is you need to differentiate this function x of t. For example, if x of t is t square, that means the particle is at the origin at t is equal to 0, it is at x is equal to 1 at t is equal to 1, x is equal to 4 at t is equal to 2, and so on. Then the velocity instantaneous will simply be dx by dt, and we know how to calculate derivatives, and it will be 2t. Right? So given the position, we'll be able to calculate the velocity. Given the velocity, we'll be able to calculate the acceleration. But we can go back in the other way as well. Given the velocity, we can calculate the position, and we know how to do that because dx, I'm just going to write v instead of v instantaneous for now. Dx is equal to v dt. From this equation, if we take dt to the other side, we can integrate both of them. And we know this to be true mathematically as well. If v is the derivative of x with respect to time, then x is the integral of v with respect to time. Right? Similarly, integral of dv, which is v, will be integral of a dt. Right? So this is for the general case. Now let's focus on the case which we are more familiar with, which is motion with a constant acceleration. So we'll start from the bottom and work our way up. We know that the acceleration is dv by dt. What that means is that the change in velocity dv is acceleration multiplied by the change in time, and then we choose to integrate it. Now we know two different ways to integrate, definite and indefinite integration, and I'm going to show you that we get the same result using both the methods. So we need an extra condition apart from this, and let's say it's given to us that v as a function of time is equal to u at t is equal to 0. That means we are given that at t is equal to 0, at the initial point, the velocity is u, which is another way of saying the initial velocity is u. So if we are given this, let's try to do it indefinitely. What will be the integral of dv? dv can be written as 1 times dv. 1 can be written as v to the power 0. The integral of v to the power 0 would be v to the power 1 divided by 1. So that would be v. So you would have v is equal to, and here is where we use the fact that the acceleration is constant. Remember, everything I'll derive from this point onwards assumes that the acceleration does not change with time. So if the acceleration is constant, acceleration can be taken outside the integral. The integral of 2 dt will be the same as twice the integral of dt. And again, dt can be written as 1 into dt, that is t to the power 0 into dt. So this becomes v is equal to 80. But since we are doing an indefinite integration, we need to remember that in indefinite integration always we have a constant of integration, and we are able to calculate the value of that constant of integration using some other conditions which might be given. In this case, we know that v is equal to u at t is equal to 0. If we substitute that, we get u is equal to a into 0 plus c, which means u is equal to c. So this particular condition, that v is equal to u at t is equal to 0, enables me to calculate the fact that c has to be equal to u, and from that I get my very familiar equation v equals u plus at. And I'm sure all of you have seen this equation before. And this equation really doesn't say anything new. All it says is that the change in velocity, which is v minus u, is equal to the acceleration multiplied by the change in time, which in this case is t, since it would be t minus 0, as the velocity is v at time t and the velocity is u at time 0. Let's try to do it by definite integration. In this case, we won't need a constant of integration because we would put the values directly in the limits. So let's say at time t the velocity is v. We know at time 0 the velocity is u. So what that means is v u to v is equal to at 0 to t. And how do we put the limits? We take the upper limit minus the lower limit. So v minus u is equal to a times t minus 0. We get the same result. V is equal to u plus at. So we see that indefinite and definite integration are two different methods of calculating the ultimate same result, which we get in both cases as v is equal to u plus at. We can integrate this equation further to calculate the displacement. We know that s and x both are used interchangeably for displacement. When it comes to the equations which you know as SUV-AT equations, s is used more frequently, so that's what I'm going to use now, but they ultimately are the same thing. So we know that ds by dt or dx by dt is equal to v, which means ds is equal to v dt. Again we can integrate, but in this case I cannot write this as vt, and the reason for that is v is not a constant now. Since the acceleration is constant, velocity is changing with time, so v would be a function of time, so we cannot take v outside the integral. But we do know v as a function of time, so v is equal to u plus at. Now u is a constant. Remember, u was the velocity at time t is equal to 0 seconds. So u is 2 meters per second or 5 meters per second. So it's a constant. A is also a constant because everything we derive, we are assuming that acceleration is constant. So, and again I could do it by both methods. In this case I'm just going to do it by indefinite and by definite integration, and ds from 0 to s becomes s, and that is equal to the integral of u dt would become ut, and the integral of at would become half at square. Since at can be written as a into t to the power 1, the integral of t to the power 1 would be t to the power 2 divided by 2. So this is the second equation. This was the first equation which we got. And if you square this equation and substitute the value of s, you can get the third familiar equation, which is v square is equal to u square plus 2as. So these are the three equations. I'm sure you've seen these before, but now we really know how to derive them, and you should try not to just remember these equations but be aware of where they came from, because right now we are doing for constant acceleration, but the moment we reach variable acceleration, there will only be one difference, which is that a will not be a constant, so it cannot be taken outside the integral. Everything else will be the same. So while calculating problems involving these three equations, there are certain things we need to keep in mind. We need to know between which two events are we applying the equation. So if we are applying the equation between t is equal to 0 and t is equal to 6 seconds, then u would be the speed at t is equal to 0 seconds, and everything else would be calculated between 0 and 6 seconds, and the acceleration would have to be constant between 0 and 6 seconds. If we are calculating the equations between t is equal to 2 and t is equal to 5 seconds, then the interval would be 3 seconds, so we would use t equal to 3 seconds, and the initial speed u would be the speed at t is equal to 2 seconds, and the final speed v would be the speed v at t is equal to 5 seconds. So before applying the equations, we need to be very clear about between which two events are we applying the equation. We need to know that we need only 3 out of the 5 equations. Out of S, U, V, A and T, once we know 3, we will be able to calculate the other 2. Okay, so let's take some cases. Let's say we know S, U and T. Using the first equation, we'll be able to calculate A. Then using the second equation, we'll be able to calculate V, and then we know everything. If we know V, U and S, using the third equation we'll be able to calculate A, and using any of the other two equations we'll be calculate whatever else is needed. So out of these 5, given any 3, we can calculate the other 2. The third thing to keep in mind is that the acceleration has to be constant between the two events. If the acceleration changes even for a second between the two events, these equations would not be valid. They are only valid since we assume the acceleration is constant and took it out of the integral. They're only valid as long as the acceleration is constant. So these are the four equations. The second equation is probably a new one, but that's nothing but saying that the displacement between two events is equal to the average velocity multiplied by the time. You can derive the equation from the other three, it would not be a problem. U plus b by 2 is the initial velocity plus the final velocity divided by 2, and that is the average velocity. So the second equation says nothing but the fact that the displacement is equal to the average velocity multiplied by the time, which is true in this case because the acceleration is linear. So let's try to use the concepts we've just learned to solve some problems. This is the problem that's given to me. This is a building with a height of 75 meters above the ground. From the edge of the top of the building, I throw an object upwards with an initial velocity of 10 meters per second. The body goes up and then it comes down. Let's call this point A, let's call this the point of maximum height as B, and let's call this point C. What I am asked is, after how much time does the object strike the ground? So the first thing to note is that we need to choose a direction for the positive x-axis. That's the first step we do whenever we define a coordinate axis. So let's take the positive axis to be upwards. Later I'll show you that even if you take it to be downwards, the equations will still be the same. The second thing we need to know is between which two events are we applying the equation. So since we need the total time of flight of the particle, the events will be, the initial event will be A and the final event will be C. We will be applying the equations between events A and C. So since the initial event is A and the velocity at A is 10 meters per second, U will be 10 meters per second. It will be positive because we've taken the upward direction to be the positive direction. The acceleration is constant between the particle being at A and C, and it is minus 10 meters per second square since the acceleration is in the downward direction. Do we know the time between A and C? We don't. That's what we need to find out. Do we know the final velocity? No, we don't know that either. We know the initial velocity at A. We don't know the velocity when the particle is at C. But remember, we need 3 and we can find out the other 2. Do we know the displacement? Yes, we do know the displacement between A and C is the height of the building. But actually it's minus 75 meters since C is 75 meters below A. We need to find out T. So we can use the second equation. Minus 75 is equal to 10t minus half into 10 into t square, which means minus 15 is equal to 2t minus t square, which means t square minus 2t minus 15 equals 0, which means t square minus 5t plus 3t minus 15 equals 0. We split the middle term, which gives me t minus 5 into t plus 3 is equal to 0, and neglecting the negative root we get t is equal to 5 seconds. So if I throw the particle upwards with a velocity of 10 meters per second, it will strike the ground after 5 seconds. Let's say we were asked to calculate the maximum height the particle has above the ground. So that means we would have to calculate this total height. Since we know the distance between A and C to be 75 meters, once we find out this height, we can just add it to 75 to get the final answer. In this case now, even though we still take the upward direction to be positive, the events have changed. Now I have to apply the equation between events A and B, right? Because I need to find the displacement between the points A and B. So in this case, since my initial point is A, U will still be 10 meters per second. Acceleration will still be minus 10 meters per second square. Do I know the displacement? No, that's what I'm trying to find out. Do I know the time between A and B? I don't know that either. Do I know the final velocity? In this case, I do. Since B is the point of maximum height, the velocity at B has to be 0. If the velocity of B was positive, then the particle would still be going upwards and it would not be at its maximum height. Similarly, if the velocity at B were negative, the particle would be descending. That means it would have been at a maximum height before that. If B is the point of maximum height, the final velocity at B has to be 0. So we can calculate the displacement using the third equation. 0 square is equal to 10 square minus 2 into 10 into s, which gives me s is equal to 5 meters. So this height is 5 meters. That means the total height is 80 meters. So we see that in both the cases we had to use this equation between two separate cases. In the first case we applied the equation between events A and C because we needed the time between A and C. In the second case we needed the displacement between A and B, so we applied the equation between A and B. If you wanted, you could try to apply the equation between B and C, and you would see that the displacement would be minus 80 meters. Another note, if we took the downward direction to be positive, U would be minus 10, A would be plus 10, and S would be plus 75. In that case, the equation would be plus 75 is equal to minus 10 plus half into 10 into t square. But we see that this equation is simply the previous equation multiplied by minus 1. All the three parts of the equation have had the signs reversed. So it will give me the same answer. Similarly, in this case also it will give me the same answer. So the first step is choose the positive direction of the x-axis. The second step is to choose two events between which you will apply the equation. The third step is, out of the 5 quantities s, u, v, a and t, just make sure you know 3 and you will be able to find out the other 2. And using this algorithm you should be able to solve any problems of motion in one dimension without much difficulty. So this completes motion in one dimension. In the next video we'll see motion in one dimension with variable accelerations, and we'll also learn how to calculate problems using graphs. Thank you.